Mapping the Milky Way. Charting the unseen. Imagine standing on a shoreline at night, gazing at the shimmering band of stars that stretches across the sky. For centuries, humanity looked up at this celestial river, calling it the Milky Way, unaware that it was but a fraction of an immense, spiraling collection of billions of stars, planets, and cosmic wonders. But here's a question. How do we map something so vast that it takes light 100,000 years to cross it? How do we chart the structure of our galaxy while embedded within it, unable to step outside for a bird's eye view? The answer is a story of ingenuity, technology, and a sprinkling of cosmic luck. The Milky Way, a galactic enigma. The Milky Way is a barred spiral galaxy, a sprawling system of stars, gas, and dark matter bound together by gravity. It's home to over 100 billion stars, including our Sun, and spans a staggering 100,000 light-years in diameter. Its structure consists of a flat disk containing spiral arms, a central bulge, and an extended halo populated by ancient stars and dark matter. The galaxy's composition reveals a fascinating interplay of elements and forces. Chemical composition. The Milky Way is primarily composed of hydrogen and helium, the lightest and most abundant elements in the universe. However, it also contains heavier elements, referred to as metals in astronomy, such as carbon, oxygen, silicon, and iron. These elements are the building blocks of planets, moons, and life itself, forged in the hearts of stars and scattered throughout the galaxy by supernova explosions. The metallicity of stars varies, with younger stars in the disk typically containing more metals than older stars in the halo and bulge. Temperature ranges. The galaxy's temperatures range widely, from the searing heat of stellar surfaces to the frigid cold of interstellar space. Stars like the Sun have surface temperatures of about 5,500 degrees Celsius, while massive, hot stars can exceed 30,000 degrees Celsius. In contrast, molecular clouds, regions of dense gas where stars form, can be as cold as 260 degrees Celsius, just above absolute zero. Supernova remnants and accretion disks around black holes reach temperatures of millions of degrees, emitting high-energy X-rays. Points of interest. Spiral arms. The Milky Way's spiral arms, such as the Perseus arm and the Scutum Centaurus arm, are dynamic regions rich in gas and dust. These arms are stellar nurseries, where dense clouds of gas collapse under gravity to form new stars. Iconic formations like the Eagle Nebula, home of the Pillars of Creation, and the Orion Nebula lie within these arms. Galactic center. The core of the Milky Way hosts a supermassive black hole, Sagittarius A*, with a mass equivalent to 4 million suns. Surrounding it is a dense region of stars, gas, and dust. Intense gravitational forces and energetic processes make this region a hub of astrophysical activity, including flares and relativistic jets. Halo. Extending far beyond the visible galaxy, the halo contains ancient stars, globular clusters, and the elusive dark matter. This spherical region provides insight into the galaxy's early history and its interactions with neighboring galaxies. Stellar remnants. Scattered throughout the Milky Way are the remnants of stars that have reached the end of their lives. These include white dwarfs, neutron stars, and black holes, as well as vast nebulae formed by supernova explosions. The Crab Nebula, for instance, is a supernova remnant that continues to fascinate astronomers. The first clues: star mapping and parallax. The journey began with the ancient Greeks, who speculated about the Milky Way's nature. However, the real breakthrough came in the 18th century when astronomer William Herschel attempted to map the stars. By counting stars in different regions of the sky, he suggested a disk-like structure for our galaxy. Yet his view was limited by the technology of his time. The 20th century brought new tools. Stellar parallax, the apparent shift in a star's position as Earth orbits the Sun, allowed astronomers to measure distances to nearby stars. This method gave us a sense of scale but could only reach stars within a few thousand light-years. The Milky Way remained largely mysterious, until we found a way to pierce the cosmic fog. Peering through the dust, radio waves and infrared light. Dust and gas, which block visible light, are transparent to other wavelengths like radio waves and infrared light. In the mid-20th century, radio astronomy revealed our galaxy's skeleton. Scientists mapped the 21-centimeter radio emissions of hydrogen gas, a primary component of the Milky Way. These signals unveiled the spiral arms and their sweeping, majestic curves. Infrared telescopes added flesh to this skeleton. By capturing the heat emitted by stars and dust, they painted a clearer picture of the galaxy's structure, revealing stellar populations hidden from visible light surveys. Infrared observations also uncovered the central bar of stars extending from the galactic core, a feature invisible to earlier astronomers. The role of variable stars and globular clusters. Variable stars like Cepheids and R. Lyrae became celestial yardsticks. These stars pulsate in a predictable manner, with their brightness linked to their intrinsic luminosity. By comparing their observed brightness to their actual luminosity, astronomers calculated their distances. Cepheids, in particular, mapped the spiral arms, while R. Lyrae stars revealed the spherical halo of the galaxy. Globular clusters, dense groups of ancient stars, provided another critical clue. In the early 20th century, American astronomer Harlow Shapley measured the distances to these clusters and discovered they formed a halo centered around the Milky Way's core, placing our Sun far from the galaxy's center. This was a humbling revelation. We are not at the heart of the cosmos. Gaia, revolutionizing galactic cartography. Enter the European Space Agency's Gaia mission, launched in 2013. Gaia has transformed our understanding of the Milky Way by measuring the positions, distances, and motions of over 2 billion stars with unprecedented precision. Imagine trying to detect a human hair from 2,000 kilometers away. That's the level of accuracy Gaia achieves. Gaia's data has not only refined our map of the galaxy but also revealed its dynamic nature. Stars aren't fixed, they move, creating a cosmic dance that tells the story of the Milky Way's formation and evolution. For instance, Gaia uncovered evidence of past collisions with smaller galaxies, which left ripples and streams of stars in their wake. Beyond the map, dark matter and the galactic halo. Yet, even with Gaia's extraordinary insights, the Milky Way holds secrets. Much of its mass is invisible, composed of mysterious dark matter. While we cannot see or directly detect dark matter, its gravitational influence shapes the motion of stars and gas, hinting at an unseen halo enveloping the galaxy. This dark matter halo may extend well beyond the Milky Way's visible edges, holding clues to the universe's most profound mysteries. Understanding it requires merging galactic cartography with cutting-edge physics, pushing the boundaries of what we know. A galactic map with a human story. Our map of the Milky Way is a testament to human curiosity and determination. From William Herschel's star counts to Gaia's billion-star survey, each step has expanded our cosmic horizons. Yet, this is not the end. The James Webb Space Telescope and upcoming radio observatories promise to uncover even more about our galactic home and its place in the universe. So next time you gaze at the Milky Way's glowing band, remember, it's more than a celestial river. It's a vast, complex galaxy we're only beginning to understand. And within it lies the ultimate question: what role do we, its tiny inhabitants, play in the grand cosmic story?